Hello everyone, I'm Norman Wahlberger and welcome to Algebraic Calculus. In this video we're going to look at affine geometry in a little bit more detail with a novel orientation to some new concepts. So affine geometry may be not quite as well studied as Euclidean geometry and projective geometry. It really deserves to be elevated a little bit in status, especially considering its very close connection with linear algebra. So let's start by just reviewing the formal official framework for affine geometry. So we'll put aside our pictures, our grid planes, our physical intuition, and just concentrate on the algebraic essentials, the actual definitions of the main objects. So I remind you that we started with affine points. An affine point was an expression of this form, two numbers, which are typically always rational numbers, enclosed in square brackets. An affine line was an equation of the form cx plus dy equals e. Again, c, d, e, and e are some kind of rational numbers, but we agree that c and d, the coefficients of x and y here, are not both zero. One of them can be zero, but not both of them. That's a line. The point lies on the line when, if you substitute these things in for x and y, then the equation is satisfied. In other words, c times a plus d times b equals e. We have a notion of parallelism of lines. So here's one line, cx plus dy equals e. Here's another line, fx plus gy equals h. We say that they're parallel when the proportion c to d is the same as the proportion f to g. And that means that c times g minus d times f equals 0. So that's the condition for parallelism of two lines. And we also had some terminology involving joins and meets. So if we have 2 points that they're distinct, then the join of them is just denoted by juxtaposition of their symbols. So AB is the line. And if we have 2 lines, L and M, then their meet is going to be LM. And that's provided that the lines are distinct and that they're also not parallel. All right, so that's just a quick review of things that we already know pretty well. Okay, so then we make the transition towards linear algebra by introducing vectors. And vectors are a measure of the relative separation between points. So officially a vector just looks like a point almost, except that it's a pair of numbers enclosed in round brackets. So RS enclosed in round brackets. Now, particular types of vectors are displacement vectors. If we have 2 points, A and B, with coordinates AB and CD, then the displacement vector AB, written with this sort of harpoon-like line over the pair, that's by definition the difference C minus A, comma, D minus B, going from A to B. So we get final minus initial, final minus initial. And now we're going to introduce some rather unorthodox notation. Okay, so we're going to introduce some new notation. That's right here. We're going to give another name for this displacement vector. So AB is one name for it, but another name will just be B minus A. So we're going to introduce this subtraction sign in the context of points. Previously, we have no algebraic structure for points. We can't add points. We couldn't subtract points up till now. But now we're saying let's agree to subtract points. We are not, however, going to agree to add points. Okay, it's just a separation that we're interested in capturing. And that's quite useful for us because in calculus we're interested in change, and change typically is represented by a difference. We're going from here to here, so the change is represented by the difference between where we are getting to and where we started from. So that idea of relative separation given by a difference is very important. We're putting our finger on it terminology-wise by introducing this terminology here. Okay, so having gone that far, let's go a little bit further and define the sum of a point and a vector. Okay, so if A is the point AB and V is the vector RS, then we are going to define what we mean by the sum of a point and a vector. A plus V, so there's A, there's V. By definition, this is the new point obtained by taking the sum of the coefficients of A and V and in both x and y places. So a plus r and b plus s. So the idea here is that a is a sort of an absolute position, v is a relative position. So if this is the absolute point A, and here is our displacement vector v, then this v is the same as that v is the same as that v. And here's our point A. If we move our vector so that it's like this, then it makes sort of some sense to say, okay, that this point plus this vector will be this object up here. In fact, if you think about it, that's exactly sort of reversing what we just did up here. Here we said that the vector was b minus a. Well, then it sort of makes sense that b, the final point, should be a plus the vector. That's exactly what we're doing. We're introducing the idea of a plus a vector. And let me also remind you that if you have 2 points, a and b, and you have the vector joining them, a, b, which we now could also call b minus a, that's a direction vector for the line AB. There's a line, a, b on it. The vector from a to b is a direction vector for the line. It encodes the direction up to a multiple. And now let's introduce another very interesting and useful way of combining points algebraically. Affine combinations of 2 points. So if a and b are 2 points, then consider for a second the expression a plus lambda, the vector ab. So ab is the vector from a to b. Lambda is some scalar or number. So this is point plus vector. So we know what that is. We have a definition of that. Now notice that ab, formerly we introduced this symbol b minus a for it to represent the fact that it's actually a difference. So it makes sense for us to be able to sort of rewrite this using the obvious laws of algebra. If we just rewrite this and write it as 1 minus lambda a, because there's an a here and a minus lambda a here, plus lambda b, then that should be the same thing. And we're going to do that, okay? So we're going to say that this particular expression is this point here. The point that you get by starting with a, here is, let's say a is at the bottom here and b is up here. So this will be the vector AB. So we're starting with A and we're adding a multiple of the vector AB. So that means we're somewhere on this line AB. We're necessarily somewhere on this line AB. And where exactly we are depends on the lambda value. If lambda is 0, then we're here. If lambda is 1, we're here. If lambda is a half, then we're here. If lambda is, say, minus a half, we would be over here. And if lambda was, say, 2 or something bigger than 1, it would be over there somewhere. So different values of lambda correspond to different points on the line. So very useful parameterization of a line through these affine combinations. Very important to note that these are not arbitrary combinations. So we're not allowed to take 2 times a plus 3 times b. These two numbers have to add up to 1. That's the crucial thing that makes this combination allowable. So we now have 2 different ways of combining points. If we have point A and B, we're allowed to take the difference, B minus A. That represents a vector. We're also allowed to take this kind of affine combination where the coefficients add up to 1, and that will then be a point somewhere on the line AB. So 2 different ways of combining points, giving us 2 different kinds of things. The difference of points is a vector. An affine combination of points is a point on the line joining them. In particular, the special case when lambda equals a half, that gives us the midpoint. So a plus a half ab, that'll be then, according to this notation, 1/2 a plus 1/2 b. And also, we could also write it as b plus 1/2 of ba. There's the vector ba. So if we start at b and go half, then we get to the same midpoint m. So it's kind of obvious, but it's important observation to make that midpoints, okay, are not intrinsically metrical notions. They're intrinsically affine notions because they can be defined affinely this way. We do not need to have a notion of distance. So I don't want you to think that the midpoint is the point where this distance equals this distance. Okay? No, distance has nothing at all to do with this. It's a question of displacement or actual vectors. It's this vector equals that vector. Now I want to introduce another new terminology having to do with proportions. So I want to talk about vector proportions, proportions between parallel vectors. So to do that, I just need to remind you that two vectors, say v equals rs and w equals pq, are parallel, pointing in the same direction, precisely when r times q minus s times p equals 0. In other words, whether the proportion here equals the proportion there, which is equivalent to saying that the lines that they generate, or lines in those directions, are parallel. So having the notion of parallel vectors, let's now talk about vector proportions. Something in the form v to w, where v and w are parallel vectors and not both 0. Okay, so it's this expression that we want to define. V and w are vectors, which are parallel, and a and b are some numbers, not both 0. So on the right-hand side, we see a familiar two proportion, a proportion between numbers. And we're defining what does it mean for that two proportion of numbers to be equal to this two proportion of vectors. The definition is that, well, it's the same thing as equality for two proportions of numbers, that b times v minus a times w should be 0. Well, the 0 vector, because these are vectors and these linear combinations will also be vectors. All right? So what we're getting at here is the idea that we could have two vectors in the same direction and we can compare their extents. For example, let's say here's one vector, v, and here's another vector, w, okay? And maybe three of these vectors make up one of these vectors. So this is v, this is w, 3 times w equals v. So then the proportion v to w, the proportion between these two vectors, is the same as the proportion of 3 to 1. 3 to 1, that proportion is the same as v to w. But it's crucial that the vectors be in the same direction for us to be able to say that. We do not define the proportion if the two vectors are not in the same direction. Okay, so then we can talk about equality of vector proportions. We can say when the proportion between these two vectors is the same as the proportion between these two vectors. Here we have two parallel vectors, say v and w. Here's another pair of parallel vectors, say u and z. When does this proportion, v to w, equal this proportion, u to z? Well, when v to w equals some proportion of numbers a to b, and that same proportion a to b is equal to the proportion of the other pair, u to z. So if both v to w and u to z are equal to the same proportion of numbers, then we'll say that these two vector proportions are themselves equal. So we're just establishing sort of transitivity between vector proportions. This is a very useful sort of technical device. So let's introduce this theorem, which we'll call Transversals to Parallel Lines theorem. It involves three parallel lines, L, M, and N, and two transversal lines, P and Q. That means that those lines are not parallel to L, M, and N. So since they're not parallel, they will meet L, M, and N, and we agree that the meets are A, B, and C for the line P, and D, E, and F for the line Q. So A and D both on L, B and E both on M, C and F both on N. So in this situation, because L, M, and N are parallel, there's a relation between the proportions involved with some vectors here. And we can express it this way, that AB to BC, this proportion of vectors, is the same as the proportion DE to EF. Okay. These two vectors are parallel, they're in the same direction. These two vectors are parallel in the same direction. These ones here are not parallel to those ones, but that doesn't matter. These two are parallel, so their proportion is well defined. These two are parallel, so their proportion is well defined. And the theorem is saying that those two proportions are going to be identically the same. So if this is 2 to 1, then this will also be 2 to 1. And no matter which line you choose here, choose one more slanted like this will still be 2 to 1. It's actually quite a pleasant little theorem. It's really a sort of foundational theorem of affine geometry. And here's a closely related theorem that's really about triangles. We could call it affinely similar triangles. In this case, we have two parallel lines, L and M, and we have still two transversals, P and Q. And they meet at some point A. And they also intersect our two lines L and M at points B and C, say, and D and E. And the theorem is that we have three equal proportions here. AB to AC. So starting with A. Okay, so AB to AC. This vector to this vector equals AD to AE. Also equals BD to CE. So what we really have here is two similar triangles. This triangle here is similar to this triangle here. And so we're stating that kind of similarity via these three proportions of the corresponding sides. But notice that we're not stating it in the form that this vector to this vector is equal to this vector to this vector. We're not saying that because we have not any way of comparing this vector with this vector. That proportion doesn't make sense. What makes sense is proportions of vectors which are parallel or in the same direction. Okay, so I think it's very interesting and useful for us to observe that we don't really need metrical geometry, like Euclidean geometry, in order to talk about aspects of similar triangles. This may not be the most general kind of similar triangles, but still these triangles are similar. So since we're framing calculus within affine geometry largely, it will be useful for us to have this kind of similar triangle formulation available to us. I'd like to finish by introducing two really famous theorems, which are also intrinsically theorems of affine geometry. And the first is Menelaus' theorem, which goes back to about 100 years after Christ. And he was from Alexandria. And actually, he wrote up this theorem in the context of spherical geometry, actually rather than planar geometry, which is rather interesting. So it concerns a triangle, ABC, together with an additional line, this line here. And this line meets the three sides of the triangle. It meets AB at this point F, it meets BC at this point D, and meets AC at this point E. So along each of the three sides of the triangle, we have 3 points, and we could talk about proportions of vectors. Okay, so let's look at the three proportions, AF to FB. So there's AF and FB. So this vector AF to this vector FB. That's a certain proportion because they're parallel. Let's say it's J to R. J and R are numbers. And then the next one, BD to DC. Kind of going around in an organized way here. BD to DC. That's also some proportion. Let's say K to S. And then finally, CE to EA. Now notice that in this case, the CE will be in that direction and the EA will be in that direction. So this proportion is going to involve a negative number somewhere in this particular situation. Okay, in any case, let's call that proportion L to T. And Menelaus' theorem says that these 6 numbers are related in this beautiful way, that J times K times L equals minus R times S times T. And in particular, if you knew 5 of them, then you could deduce what the 6th one is very easily. Now, Menelaus' theorem is usually presented, often presented, as a theorem in Euclidean geometry. It's not intrinsically a theorem of Euclidean geometry, and it's a little bit awkward to try to prove it in Euclidean geometry because you end up talking about distances, and distances are just not really the right notions for this theorem. It really wants to be about vectors with directions and not just lengths. In fact, the lengths are irrelevant, really. They're related, but they're irrelevant. You don't need a theory of lengths. You just need the underlying affine geometry. And this formulation involving these vector proportions, I think, really brings that out. And also gives us an opportunity of saying, well, how are we going to prove this within the context of affine geometry? Now, there's a closely related theorem due to G. Ceva in around 1678. So quite a long time after Menelaus. And it's very similar. It deals with the triangle ABC, but now instead of an additional line, there's an additional point. Okay, and the additional point allows us to draw these three lines, sometimes called Cevians. AK, which meets the opposite side of the point D, BK, which meets the opposite side of the point E, and CK, which meets the opposite side of the point F. So we still get 3 points on the sides of the triangle, but now sort of starting from a point rather than a line. And otherwise, the formulation of the theorem is very similar except to the punchline. Okay, so we're introducing exactly just as before. AF to FB is J to R, BD to DC is K to S, and CE to EA is L to T. And then Ceva's theorem is that the product JKL equals the product RST, this time without a minus sign. This is a very beautiful theorem. It's very useful. It's probably more commonly used than Menelaus' theorem. And it's intimately connected with the theory of centers of mass and balancing, as we'll see. So it's a lovely result, and also essentially really part of affine geometry. So I'm trying to convince you that affine geometry is actually a very rich subject, and there's lots of interesting things happening there. We have enough technology, terminology to set up calculus. It's rich enough to support a very good calculus. So there's much to learn. I'm Norman Wildberger. Thanks for listening.